What's up, everyone? In this episode, I'm going to demonstrate how to use equilibrium conditions to solve any problems in statics. Again, I always start with basics. So today's video only covers the guide to use two-dimensional equilibrium conditions. In the future episode, I will talk about the problems that use three-dimensional equilibrium conditions. Let's get started. In two-dimensional case, forces acting on any object will be on the plane. Conventionally, we prefer using plane that is enclosed by x and y axis, and z-axis points normal to the xy plane. Therefore, no matter where a force points to, it can always be decomposed into an x component and a y component. Now, let me officially introduce you the superstar in statics, the equilibrium conditions. There are three equilibrium conditions in two-dimensional case. Number one, the sum of all x components of forces is equal to 0. Number two, the sum of all y components of forces is equal to 0. Number three, the sum of all moments is equal to 0. The purpose of using equilibrium conditions is to solve unknown forces and sometimes unknown moments. Pretty much 99% of the time, you shall first solve unknown forces at the supports by using equilibrium conditions. We usually call forces at the support as reactive forces or reaction forces. I'll use the term reaction forces in this video. Once the reaction forces are determined, you then solve the rest of unknown forces or moments by using equilibrium conditions. Remember, you must draw free body diagram before you can use the equilibrium conditions. Notice there are only 3 equations in two-dimensional equilibrium conditions. Therefore, the maximum number of unknown forces and moments you can solve simultaneously is 3. If there are more than 3 unknowns in one free body diagram, you come across a problem called statically indeterminate problem. I'll definitely cover it in the future episode. Now, we're only going to see statically determinate problems. Before we start, let's make sure that we all agree with the sign convention in statics. For forces, they are positive if they're towards to the positive direction of x and y axis. For moments, they're positive if they have tendency to make objects rotate in counterclockwise direction about an axis. Let's take a look at an example. Example 1. In any truss problem, if it asks you to determine the force in each member of the truss, we prefer using the method of joints. This is the general procedure of the method of joints. Number 1, draw the main free body diagram. Number 2, apply equilibrium conditions and determine reaction forces at supports. Number 3, draw free body diagrams for each joint. Number 4, apply equilibrium conditions for each joint and determine forces in each member. Step 1, draw the main free body diagram. Step 2, apply equilibrium conditions and determine reaction forces as supports. Here, there are 3 conditions. It doesn't matter which conditions apply first, but in situation where there is a pin support that generates 2 unknown reaction forces, we prefer applying moment condition about that pin first. This is because moment of force about specific point will be 0 if that force passed through that point. So if you apply moment about E, the moment of these two unknown reaction forces, Ex and Ey about E, are 0, which left only one unknown, Ax, to be solved. Sum of the moment about E is equal to Ex times 0 plus Ey times 0 plus Ax times dAe minus 4 kilonewton times dEd minus 4 kilonewton times dAc minus 2 kilonewton times dEd times sine 60 degree equals to 0. Now we have to calculate the distance. dAd, based on trigonometry, 2 divided by cosine 60 degree, which is 4 meters. dAe equals sine 60 degree times dAd, which is 2 square root of 3 meters. dEd equals 2 meters, and dAc equals 8 meters. Sum the moment about E, and then we can solve Ax as 12.547 kilonewton. Once the reaction force Ax is solved, decompose the force at D into x and y component as Fdx and Fdy. Fdx is adjacent side relative to the given angle. Thus, Fdx is equal to cosine of 60 degree times Fd. So Fdx equals 1 kilonewton. Fdy is opposite to the given angle. Thus, Fdy equals sine 60 degree times Fd, which is 1.732 kilonewton. Now, sum the forces in x direction. We have sum Fx equal to Ax minus Fdx plus Ex equal to 0, which give us Ex is equal to negative 11.547 kilonewton. Here, negative sign means the actual direction of the force is opposite to the direction where arrow of Ex points to. You can keep the original direction of the arrow as long as you keep the negative sign in calculation. So don't get bothered by it. Sum the forces in y direction. We have sigma Fy equals to negative 4 minus 4 minus Fdy plus Ey equal to 0. We know Fdy is 1.732. So we can solve for Ey as 9.732 kilonewton. Now we solved all unknown reaction forces. Move on to step 3. Draw free body diagrams for each joint. Here we have joint A, B, C, D, and E. We should always start with the joint that has the most reaction forces. So let me start drawing free body diagram for joint E. Then draw a free body diagram for joint A. Next, we draw a free body diagram for joint B. Then we draw a free body diagram for joint C. Lastly, we draw a free body diagram for joint D. Step 4. Apply equilibrium conditions for each joint and determine forces in each member. We start from applying equilibrium conditions for joint E. In free body diagram for joint E, we already know Ex equal to negative 11.547 kilonewton and Ey equals 9.732 kilonewton. Sum all the forces in x direction. Sigma Fx equal to Ex plus Fde equal to 0. We know that Ex equal to negative 11.547. So we can solve for Fde as 11.547 kilonewton. And we also know the member DE is in tension because FDE is positive. So the actual direction is the same as the direction of the arrow. Thus, it's stretching the member. So it's in tension. This is another tip. So in free body diagram, when you keep the force in member away from it, and later in calculation, if you get positive value, it means the member is in tension. Otherwise, it's in compression. Next, we sum all the forces in y direction. Sigma Fy equals to Ey minus Fae equals to 0. Since we already know Ey as 9.732, we can solve for Fae, which is 9.732 kilonewton. And it's positive, so is in tension. Now, applying equilibrium conditions for joint A. We already know Ax is 12.547 kilonewton, and Fae, which is 9.732 kilonewton. And notice that in x direction, there are x component of FAD and FAB, which are unknowns. And we only have one equilibrium equation for x direction. Thus, it's impossible to solve two unknowns. But if you look at all the forces in y direction, there is only y component of FAD is unknown. And we can apply equilibrium equation for y direction to solve it. Therefore, we sum all the forces in y direction first. Sigma Fy is equal to Fae plus sine 60 degree times FAD equals to 0. Since we already know Fae as 9.732, we can solve for FAD, which is negative 11.238 kilonewton. Since it's negative, the member is in compression. Then we sum all the forces in x direction. Sigma Fx equals to Ax plus Fab plus cosine of 60 degree times FAD equals to 0. We already know Ax as 12.547. And also we know FAD, which is 11.238. So we can solve for FAB, which is negative 6.928 kilonewton. Since it's negative, the member is in compression. Now, applying equilibrium conditions for joint B. We already know FAB, which is negative 6.928 kilonewton in compression. Sum all the forces in x direction. Sigma Fx equals to negative Fab plus Fbc equals to 0. Since we know Fab, and we can solve for Fbc, which is negative 6.928 kilonewton. Since it's negative, it's in compression. Sum all the forces in y direction. Sigma Yf equals Fbd minus 4 equals to 0. Thus, Fbd is 4 kilonewton. Since it's positive, it's in tension. Now applying equilibrium conditions for joint C. We already know Fbc is negative 6.928 kilonewton and is in compression. Sum all the forces in x direction. Sigma Fx is negative Fbc minus cosine 30 degree times FCD equals to 0. Thus, FCD is equal to 8 kilonewton. Since it's positive, it's in tension. Now, we have found every single force in each member. Notice that we don't need to apply equilibrium conditions to joint D anymore, because all forces will automatically satisfy the conditions. But during the exam, you can use joint D to verify if your answers are correct. Okay, this is the end of the video for you guys today. Hopefully now you know how to apply equilibrium conditions to solve two-dimensional truss problems. And In this episode, I introduced the method of joints to determine the force in each member. In fact, there is another popular method that engineers use. It is called the method of sections. I'll cover it in the next video. If you think you have learned something, please give this video a thumbs up and subscribe the channel. Stay tuned and may the force be with you. Peace.